Anyway, today we're going to talk about graphing rational functions, which is part of the reason, well, not the only reason we talked about graphing polynomials last time, was because a rational function is just a polynomial divided by another polynomial. That's what it means to be a rational function. Now, I will tell you, just so you're aware, people do abuse this language. You will have teachers later on probably think a rational function or a rational expression, and it won't actually technically be, because there might be like a square root in the top or a sine or cosine in the bottom. But specifically, when someone says a rational function and they actually mean it, they mean a polynomial divided by another polynomial. That is the actual definition of a rational function. So here's some examples. We've got x squared divided by x to the 6 minus 1. We've got x squared plus 1 over 3x squared minus 1. You've even got 4 over 3x squared minus 1. All these are examples of rational functions because they have a polynomial divided by another polynomial. And we'll remind everybody, yes, 4 is a polynomial. It's just a boring 0-degree polynomial, but it's still a polynomial. One other example that I want to write on here that you wouldn't normally write, I could say, here's another rational function, g of x equal to x squared plus 3 divided by 4. But I wouldn't actually call that a rational function because you could really just write it as a polynomial. You could say, oh, I have each thing divided by 4. So that's equal to x squared over 4 plus 3/4, or really just 1/4 x squared plus 3/4. I just want to point out that that is technically just a polynomial. It's a parabola if we graph it. So if your bottom polynomial has degree 0, then really your thing is a polynomial, not a rational function. But usually we're not going to see examples like that where you have like a polynomial divided by 2. Or if we did, we would just simplify it. All right. So when we graph polynomials, we're going to do, sorry, not polynomials, we graph rational functions. We're going to do a lot of the same stuff we did for graphing polynomials, which is find the x-intercepts and the y-intercepts. Additionally, after we do those two things, there's two other things we're going to look for when we're graphing rational functions. And that is not first, but one of the things we're going to look for is vertical asymptotes. So the way we find vertical asymptotes are by setting the denominator to 0. So to find them, you're going to set the denominator of your rational function equal to 0 and solve. I should also point out a vertical asymptote is a vertical line that is not actually part of your graph. Right, so there's going to be this, usually we draw it dashed when it's an asymptote, whether it's horizontal or vertical. We're going to draw a dashed vertical line, but really the graph is kind of just, it's helping us display the behavior of the graph. For example, this function, f of x equal to x squared minus 1 over x plus 2 times x minus 3. Someone was nice and already factored it for us. All we would do here is look at the denominator if we wanted to figure out what was going on with the vertical asymptotes. So we would just set the denominator equal to 0, x plus 2 times x minus 3 equal to 0, and we would get x equal to -2 as one of our vertical asymptotes, and x equal to +3 as the other vertical asymptote. So these would be our vertical asymptotes. Which I'm going to abbreviate because vertical asymptotes, too long words to write. I will point out there's one kind of additional thing you technically have to do, which is before you look for the vertical asymptotes, you should actually factor both the top and the bottom and cancel out any common factors. I'll remind you that I think it was when we talked about piecewise functions, we did see that if you had some factors cancel, you end up getting a whole. So just be aware that it's usually not going to come up, but sometimes you should, or you should always really factor and cancel any common factors before you start mapping stuff. We may look at an example like that. Again, it's not a huge deal, but I don't want to lie to you and say it never happened. So, typically, we don't cross vertical asymptotes, right? You can't, like, it's kind of a hard barrier. Someone, if they really, really wanted to, could make up a really dumb graph where you cross the vertical asymptote. You're never going to see that. So don't worry about it. And then, let's see, anything else I want to say about vertical asymptotes? Okay. Any questions so far about vertical asymptotes? We'll talk about it. We've actually seen some graphs already with vertical asymptotes, like 1 over x and 1 over x squared. They both had vertical asymptotes. As you got closer and closer to 0, the graph went really, really vertically high, or one side went down. We'll talk more about the behavior in a minute. The other sort of asymptotes that rational functions typically have or horizontal asymptotes. So a horizontal line would form y equals a constant. And to find a horizontal asymptote, there's actually a little bit more work we have to do, or a little bit more thought we have to give. So what we have to do is consider the degree of both the top and the bottom of your rational function. There's three possible things that can happen when you compare the degree. Remember, I'll remind you, the degree is just the highest power of the polynomial. So just to look back here for a second, for this rational function here, the degree on top is 2, the degree on the bottom is 6. For this rational function, the degree on top is 2, and the degree on the bottom is 2. And for this rational function, the degree on top is 0, and the degree on the bottom is 2. So just whatever the highest power of x is in each part. So to find the horizontal asymptotes, first thing that could happen is, what if the degree on top is less than the degree on the bottom? Well, if that's the case, then the horizontal asymptote is just the x-axis, or the line y equals 0. Oops, come on in. So we've already seen examples of this, like 1 over x and 1 over x squared. Those are both examples of functions that have y equals 0 as the horizontal asymptote. Again, we're going to see some examples in just a minute. I'm going to write this other stuff down. The second thing that can happen is the degree on top could be greater than the degree on the bottom. If that's the case, you actually don't have a horizontal asymptote. Bless you. Here's what I would think about in both of these cases so far. If the degree on the bottom is larger, what that means is the bottom thing is a bigger thing, or a thing that grows faster. You can think of this first example up here, x squared over x to the 6 minus 1. In this rational function here, if you plug in like x equals 10, the top's going to be 100, and the bottom's going to be 1,000,000. 100 over 1,000,000 is super duper small. So for something like this, where the degree on the bottom is larger, the whole fraction is going to get smaller and smaller and smaller because the bottom part is so much bigger than the top part. And then the reverse is true if the degree on top is larger. If you flip this over and said you had x to the 6 minus 1 over x squared, then the top would be getting really, really big, and the denominator would not be getting very, very big, and so your fraction would be getting very, very large. That's what's kind of happening with those two examples. And so when you don't have a horizontal asymptote here is because what's going to happen is x is really large, your function is just going to grow larger and larger and larger. It's not going to get close to any one particular value, which is what it means to have horizontal asymptote. Finally, the one that's kind of the most fun is when they're equal. So if the degree on top is equal to the degree on the bottom, then the horizontal asymptote is y equal to the leading coefficient on top divided by the leading coefficient on the bottom. And this last sentence on this first page is kind of super important. So what it says is the function will approach, meaning get closer and closer and closer to the horizontal asymptote for values of x that are really, really negatively large or really, really large. It's possible for the function to cross the horizontal asymptote, and we won't talk about that too much, but I will definitely show you some examples where a function crosses its horizontal asymptote. It's totally valid. It happens all the time. All horizontal asymptote means is as you go way, way, way out that way, or way, way out that way, the function gets closer to this particular value. But it doesn't really say anything about what's happening in the middle of the graph. Questions so far? Okay, that's all the preamble. The rest is just doing examples. So we'll do some graphs and we'll talk about how to find the horizontal asymptotes and vertical asymptotes. And please, 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 if you have questions about what we're doing, don't hesitate to ask. So let's look at this next example. We're going to graph x plus 6 over x minus 2. And I'm going to start with the usual things. I'm going to start by finding the intercepts. So I would say the technique for graphing any rational function, I guess I can look at my previous notes, is to find the y-intercept by setting x equal to 0. And then we're going to find the x-intercepts by setting y equal to 0, or the function equal to 0. So let's start with those two things. I think this pen is dying. So y-intercept easy. If I set x equal to 0, I'm going to get f of 0 equal to 0 plus 6 over 0 minus 2, which is 6 over negative 2. Oh, sorry, I didn't put the things up. Good. I see you looking around. Oh, I forgot to bring all of them. Here's the one. Apologies. Only one today. Those of you on Zoom, something else I got to give you that. You can also fill out the attendance form later. You can get it from Canvas. And also, if it didn't happen, it wouldn't be the end of the world because attendance doesn't count. But please do fill it out, even though I said it's not a big deal. 6 divided by negative 2 is negative 3. So there's my y-intercept. You could write it down as 0, negative 3, just to be super specific. Okay, x-intercepts of rational functions are kind of, there's something to say about them. Yes, we're going to set the function equal to 0. So we're going to set x plus 6 over x minus 2 equal to 0. And here's what I want everybody to see. The first thing you should always do for this is multiply both sides by the denominator. So I multiply both sides by the denominator. I have x minus 2 times x plus 6 over x minus 2 equal to 0 times x minus 2. 0 times anything is 0. And the whole point of multiplying by x minus 2 on the left was to cancel the denominators. So the x minus 2 and x minus 2 cancel out. And so what ends up happening is you end up just setting the numerator equal to 0. And so if you want for a rational function, you can always skip the step of setting the whole thing equal to 0 and jump to setting just the top equal to 0. So I'm going to write that over here. So you can set the whole function equal to 0 or just set the numerator equal to 0. And the thing I always say to myself when I do this is, oh yeah, if I want a fraction to equal 0, the only way a fraction equals to 0 is if the top is equal to 0 and the bottom isn't. All right, so now time for the asymptotes. I typically like to look at the vertical asymptote first, not for any good reason, it's just how I've always done it. So for the vertical asymptote, we're going to set the denominator equal to 0. So let's see over here. Setting the denominator equal to 0. That's not too terrible here. Set x minus 2 equal to 0. We get x equal to positive 2. Oh, I didn't finish the process over here. Sorry about that. Setting this one equal to 0, we're going to get x equal to negative 6. And that's our x-intercept. So for x equal to 2, that's our vertical asymptote. It's going to be a vertical line. And then finally, for the horizontal asymptote, there's not like a good do the thing, right? It's very much you have to be more thoughtful. So I would say the idea here is to look at the degrees. So for my function, x plus 6 over x minus 2, I see that the degree on top and the degree on the bottom are both 1. So degree on top and the degree on the bottom match. Degree on the top equals 1, which equals the degree on the bottom. So after I have noticed that the degrees are the same, then I'm going to say, okay, well, now I'm going to look at the leading coefficients. So, and this is where maybe this is not the best example because they're kind of the same as the degrees. So I'm going to write this out in a very kind of annoying way. I'm going to write this out as 1 times x to the first plus 6 over 1 times x to the first minus 2. You should never write it this way. It's super annoying. But what I want to point out is the degrees are the same, 1, 1. So the horizontal asymptote is the fraction or quotient of the leading coefficients, which also both happen to be 1s. So here, our horizontal asymptote is going to be y equal to 1 divided by 1, which is y equal to 1. Great, we have all the pieces. Now we're going to graph the thing. So I would say we're going to put all of our points on our graph and all of our features, and then we'll try and graph the graph. So let's see, I've got x equal to -3, or sorry, y equal to -3 is my y-intercept. I've got x equal to -6 as my x-intercept. Might be where I might not be super precise. And then I've got x equal to 2 as my vertical asymptote. So I'm going to draw a dashed line. I don't think you need to use a different color, but I'm going to use a different color just for the fun of it. So here's my vertical asymptote. X equals 2. I do like to label it. And then my horizontal asymptote is going to be y equal to 1. Okay. Some interesting things to be aware of when you graph this. I would always encourage you to start at your y-intercept. I'm going to start right here. And now here's a fun fact about vertical asymptotes. As you get closer to them from either side, you have one of two choices. The graph either has to go down, 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 down to negative infinity, or up, 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 up to positive infinity. Those are the only things that can happen as you get closer to a vertical asymptote. We'll talk about why in just a second. But let's just think about what we have to do if we start here at the point 0, -3. If I start moving towards the right, can I go up to infinity, or do I have to go down to negative infinity? I have to go down to negative infinity. Now, the question is why? And I'm going to tell you all the answer is not because I can't cross a horizontal asymptote. The answer is because I can't cross the x-axis. I don't have an x-intercept, and I have to have an x-intercept if I'm going to cross the x-axis. So I can't go this way because there's no x-intercept between 0 and 2 here. So I'm stuck going the other. And usually the x-axis is a real kind of barrier saying, oh, if you don't have an x-intercept, you can't cross it. So we have to go down this way. Like that. Now, on the other side of 2, like if I pick x equal to 3, the question is, am I still going down this way, or am I going up this way? There's a couple of ways to figure this out. One way is just to plug another point in. Kind of not my favorite, but it is a way of doing it. So if you plugged in x equal to 3, right, there's my graph again, right? So if I set x equal to 3, I would get y equal to 3 plus 6 over 2. Sorry, over 3 minus 2, which is 9 over 1, which is 9, which is positive. So I can see that if x is 3, y is going to be 9, I'm going to be going way up this way. The other way to see this, which I like less, or which I like more, but I feel like it's not always super straightforward, is to actually look at the multiplicity of the asymptote. So this asymptote, x equal to 2, came from this factor, x minus 2, which had what multiplicity? 1. When vertical asymptotes have odd multiplicity, they do the opposite thing on either side. On the other hand, we'll see an example where if they have an even multiplicity, they do the same thing. It's kind of like how when intercepts have an even multiplicity, they bounce, and when they have an odd multiplicity, they cross. It's a similar-ish idea, but again, it's probably easier just to pick another point. That's what I would probably say I would do. And then as we move further to the right, we have to get closer and closer and closer to this horizontal asymptote. On the left-hand side, I have to hit that point there, and I can't bounce off. Well, because one, it's an intercept that came from a factor with an odd multiplicity, and two, because I have to get closer to this horizontal asymptote as I go way to the left. So what's going to happen is we're going to go this way, and we're going to cross at that intercept. You get closer and closer and closer to y equals 1. Well, I should label this as y equals 1. So a couple things I would like to point out. If you look at this function, f of x equal to x plus 6 over x minus 2. If you picked a really big value for x, you would get a number for y that was very close to 1. For example, I'm going to pick something easy. Well, if I picked, say, like x equal to 1,002, then f of 1,002 would be 1,002 plus 6, which is 1,008, over 1,002 minus 2, which is 1,000, which is 1.008, which is pretty close to 1. So as you pick values for x that are really, really big, or really, really negatively big, the y values are getting super duper close to the horizontal asymptote, which is why we draw the horizontal asymptote, help us graph that. On the other hand, if you pick values of x that are super duper close to 2, like now these are going to get a little bit messy here. Let's say we pick x equal to 2.001, for example. If I plug that in, f of 2.001 is going to be 2.001 plus 6 divided by 2.001 minus 2, which is going to be 8.001 divided by 0.001. 0.001 is not 1/10, not 1/100th, it's 1/1000. So this is really 8.001 divided by 1/1000th, which is like multiplying by 1,000. This is 8,001, which is really big. So the whole point here is that as my x values get really close to 2, my y values are going to get super duper large. Or I'm not going to do it, but I will tell you, if I pick x values that was really close to 2, but on the other side, so I picked like 1.999 and I plug that in, I would get a super big number, but it'd be super negative. So on one side of 2, we're going way up to infinity. On the other side of 2, we're going way down to negative. Okay. Before we do another example, let me ask y'all questions, comments, thoughts. Zoom as well.
Divide on the one above it where f equals 1,002.
When I plugged in 1,002, yeah, I did the division.
At the end, you divide the 1,008 by 1,000.
Correct, yes. And 1,008 divided by 1,000 is just 1.00. Really, I'm just kind of cheating, saying, right, I'm dividing by 10 3 times, so I'm moving the decimal place over 3 times. Other questions? So you don't have to do any of this work of plugging in really big numbers or numbers really close to your vertical asymptote. I'm just trying to show you that that's why we have these things. So when x is really big, the y values are very close to 1. Or when x is really close to 2, the y values are very large or very negative large. But there's no expectation that you actually plug in numbers to show that. Let's look at another example. Again, got questions or thoughts or concerns? Just ask. Oh, I'll come back to that. Sure. So let's look at this next one, which is 2x squared divided by x squared minus 1, I think, right? Yeah. Yes. And before we get going here, I would just note that the degree on top and the degree on the bottom are the same, right? The degree on top is 2, the degree on the bottom is 2. That'll definitely look really good. Okay. Not really good. All right, same stuff as before. Find my y-intercept. I'm going to set x equal to 0. I'm going to get f of 0 equal to 2 times 0 squared over 0 squared minus 1, which is 0 over negative 1, which is 0. Now, the y-intercept being 0 means an x-intercept is also going to be 0. There might be more x-intercepts. We're definitely going to get 0 as an x-intercept because we've got the origin. I think that's going to be our only one, but let's make sure. So for x-intercept, we're going to set the top equal to 0. That's going to give us 2x squared equal to 0, which is going to give us x squared equal to 0, which is going to give us x equal to 0. So yes, you just get 0. Okay, that's a weird look. Okay. So our only intercept is the point 0, 0. Might make it hard to graph. Let's find the vertical asymptotes. So we're going to set the denominator equal to 0. And I would, even though you could add 1 and take the square root of both sides, I would really encourage factoring instead. Totally fine to do it the other way, but factoring allows us to maybe see some other stuff. Those factors is x minus 1 times x plus 1 equal to 0, and x minus 1 equal to 0 is going to give us x equal to 1, and that's going to give us x equal to minus 1. So those are my vertical asymptotes. And here's the observation I'm going to make. Both of these asymptotes came from factors with odd multiplicities, which means each of these vertical asymptotes is going to do a thing like this, or one side's going up to infinity and one side's going down to minus 1. Or as I like to say, Odd multiplicities for asymptotes give you opposite behavior. Odd, opposite. Let's start with O. Kind of works. Oh, I also should have said that this x-intercept here, x equal to 0, is coming from a factor with an even multiplicity. So this is actually going to have an even multiplicity of 2, which means we're going to bounce at this x-intercept. That whole multiplicity thing for x-intercept still works even if you're dealing with not polynomials. If you're dealing with rational functions, it's still a valid thing to look at. All right, lastly, horizontal asymptote. The degree on top is 2. And the degree on the bottom is also 2. So when the degrees are the same, we then look at the function and say, okay, I've got y equal to 2x squared over x squared minus 1. And my leading coefficients are 2 on top, and I didn't write it, but I'm going to write it now, and 1 on the bottom. So my horizontal asymptote is going to be y equal to 2 divided by 1, which is just 2. I want to be extra clear though. I'm not looking at the degrees to like divide degrees or say the degree is 2, so it's y equals 2. I'm looking at the leading coefficients of those highest power terms and then dividing those by each other. Okay. Got all the information I could possibly glean from this. So now we're going to try to do our best to graph it. We might need to plot some extra points here, but we'll see. So say I got the origin. That's my only point. And I've got a vertical asymptote at 1 and at -1 and a horizontal asymptote at 2. So here's all I've got so far. There's my horizontal asymptote at y equals 2. There's my vertical asymptote at x equals 1. Now here is what's kind of a bummer about having the origin as our y-intercept as opposed to some other point. I don't know from right here if I should be going up or I should be going down. Because I'm not starting above or below the x-axis, I'm on the x-axis. And even though it would be really nice to say, well, I can't cross a horizontal asymptote, that's not true. I can cross a horizontal asymptote. I don't think I do here, but I should probably check. So what I'm going to do is actually check another point. I'm going to plug in like something between 0 and 1, like 1/2. So if I look at my function, which is f of x equal to 2x squared over x squared minus 1, and I plug in 1/2, f of 1/2 is going to be 2 times 1/2 squared. And again, I'm not really looking for the value so much as I'm looking for whether it's positive or negative. I just want to know if this thing goes up or down. So then I plug in negative 1/2, sorry, positive 1/2 still, and I get 1/2 squared minus 1. The top is for sure positive. It's 2 times a fourth. The bottom, on the other hand, is negative because 1/2 squared is 1/4, and 1/4 minus 1 is for sure negative. This ends up being 2/4 over -3/4, which is -2/3. But again, I really only care that it's negative because I'm not actually going to plot that point. I'm going to say, okay, great. As they go to the right, it has to be negative. And then once I'm down here, I'm stuck. I have to be down. As I keep going to the right, so I'm always thinking of going from left to right, kind of. On the other side of this vertical asymptote, we can either say, well, we know it's going to be positive because we said our vertical asymptotes both did the opposite thing, or you could test another point. If I plugged in, 2, I can see that the top's going to be positive, it's going to be 8. The bottom's going to be positive, it's going to be 3. Positive, both things positive. Now we have to do the other side. Couple things we could do to do the other side. Well, one, we know it's going to bounce at the origin because we said it was a thing with an even multiplicity. Or you could plug in a point like -1/2, but you're going to get the same results. The other thing you could see if you had keen eyes, what we're looking for it, is that this function's even. If you plug in a -x, you get 2 times -x quantity squared over x, -x squared minus 1. That's the same thing you started with. So you're going to have this symmetry about the y-axis. So it's actually going to do this kind of deal, just like that. And then like that. Whoops, except, it should actually look symmetric if you say it's symmetric. Close enough. I don't think you need or should necessarily be looking for that even or oddness, but if you happen to notice it, you can certainly use it. Be like, oh, this thing has symmetry across the y-axis. I'm going to use that fact to make it easier to graph. Or we could have just said, we know it's going to bounce here, so it's going to do that. And we know that this vertical asymptote also has the opposite kind of behavior, so it's got to be up here. Something to be aware of, or something I've seen in the past, is I've seen like kind of this whole part here get forgotten. To make sure that when you're graphing these things, kind of the only x values that should be missing from your graph are where you have vertical asymptotes. So I don't have, a point when x equals 1 or when x equals -1. I should have labeled those vertical asymptotes, by the way. X equals 1, x equals -1. But every other x value should have a corresponding y value. So make sure we get all those. Yeah, and then I should also say, when you're graphing it, make sure the thing you're graphing is a function, meaning it should be passing the vertical line. I shouldn't have something up here and also down here. And then, not that I'm expecting that, just I'm speaking from experience, what I've seen in the past. So here. Cool. All right. More examples. Examples. I think the next one on there is x minus 3 over x squared plus 2x plus 1. Does that look right? Okay, cool. So it's the same process every time. It's the same 4 things we're looking for. So it's always y-intercept, x-intercepts, vertical asymptotes, horizontal asymptotes. Something I would say is that the x things, meaning the x-intercepts and the vertical asymptotes, right? Because the vertical asymptote is an x equals something, are usually easier to get if it's factored. Meaning the top is factored, the bottom factored. Whereas the y things, like the y-intercept and the horizontal asymptote, usually easier to see if it's not factored. Here's what I mean. We could totally factor this. This is equal to x minus 3 over x squared plus 2x plus 1 factors as x plus 1 times x plus 1 or x plus 1 squared. If I was doing the y-intercept, where I set x equal to 0, not that it's a whole lot harder to do it for the second one, but it's, I think, easier to plug it in here. If I plug it in there, I just get -3 over 1. Or if I plug it in here, I have to do a little bit of work. It's 0 plus 1 and then 1, right? It's not like but it's easier if it's not factored when you're trying to find the y stuff. So I say x equals 0, I'm going to get y equal to 0 minus 3 over 0 plus 0 plus 1, which is -3. Great. So 0, -3 is my y. Find the x-intercept. We're going to set the top equal to 0. Which means we're going to get x minus 3 equal to 0, which becomes x equal to 3. So our x-intercept is the point 3, 0. Vertical asymptotes. We're going to set the bottom equal to 0. And I do think it's worth studying the factor formula. So I'm just going to set x plus 1 squared equal to 0. I don't feel like I really need to do any work after that. The only solution there is going to be x equal to -1. You could you take the square root of both sides and then subtract 1 from both sides. But I don't think you need to show that. You can say, okay, we know x equals -1. I'm going to point out this x equals -1 came from this factor, which was to an even power. So x equals -1, this vertical asymptote has a multiplicity of 2. Or an even multiplicity, meaning both sides are going to be doing the same thing. They're going to be both going up or both going down. Yeah. The way I really think about that, to be honest, is even multiplicity things, you're always staying on the same side of the x-axis. So for x-intercepts, when you have an even multiplicity, you bounce off the x-axis and either stay above if you're already above or stay below if you're already below. Same thing is true for vertical asymptotes. If your vertical asymptote has an even multiplicity, you are both going up because you're staying on the same side above the x-axis, or you're both going down, staying on the same side below. And then the opposite thing is true for odd multiplicity. For intercepts, you cross, meaning you go from above to below or below to above. For asymptotes, you do the opposite, meaning if you were above, then you're below, or vice versa. It's kind of neat. Kind of a lot to say though. So, horizontal asymptotes. All right, well now the degree on top is What is it? And the degree on the bottom is 2, right? No matter which way you write it, even if it's x plus 1 squared, it's still degree 2. And that's definitely less. So when the degree on the top is less, that means our horizontal asymptote is y equals 0. And again, the way I would encourage you to think about that is, oh yeah, when the x values are getting very, very large, the fraction is going to get super duper close to 0 because the bottom is going to be so much bigger than the top. Also, in general, that's just a good, like, you're going to see this a lot in calculus, thinking about like fractions and what's happening as x is big. If you have fractions, when the top gets, or sorry, when the bottom gets big, the fraction is going to get small. And when the bottom gets small, the fraction is going to get big. It's that whole inverse relationship thing. That comes up a lot, so I would encourage you to get really comfortable hearing that, saying that. Yeah. All right, let's graph this thing. So I'm not going to draw the horizontal asymptote because it's kind of already there. I don't like drawing a dashed line on top of my x-axis, but you certainly can if you like to. I don't like to. Vertical asymptote, x equal to -1. I was doing them in red. Oh, well. So my vertical asymptote is x equal to -1. X-intercept at 3, 0. Y-intercept at 0, -3. Okay. Oh, sorry, you can't see that. You want to see the things I'm actually doing. Right. So I've got all the stuff, and again, right, I guess I could say y equals 0. I could label it. So. Starting at my y-intercept, I usually like to go to the right. I guess I will. So as I go to the right, I have to kind of hit all the features that are there. So the only feature I see first is my x-intercept. And I'm going to cross my x-intercept because, well, my x-intercept came from setting x minus 3 equal to 0. And that's an x minus 3 with an odd multiplicity. If you don't like that, you could also just test another point, right? If you're saying, well, okay, I know I'm below the x-axis here. If I plug in 4, 4 minus 3 is positive, and the bottom is definitely positive because it's something squared. So it's definitely going to be positive. So here's where things are going to get a little bit dicey. We're going to cross, but then what happens after we cross? We keep going up and up and up. No, we have a horizontal asymptote that we have to get closer and closer to. So what has to happen is we have to turn around. Instead of getting bigger, we have to start getting smaller. We don't know where that turnaround point is. Just make it up, right? Just draw it so it doesn't look super dorky. Do it like that. Because we know at the end of the day, we have to be getting closer and closer to the horizontal asymptote. And then I'm going to go back to my y-intercept and go the other direction. So instead of going to the right, now we're going to go to the left. And as we go to the left, the thing we're going to come up against is this vertical asymptote. And we only have 2 choices when you come up to a vertical asymptote. You either go up to infinity or down to negative infinity. And certainly it looks like we're going to be going which way? Down to negative infinity. We can't go up because we can't cross the x-axis where there isn't an x-intercept. Oops. And then on the other side of x equals -1, you can either use the observation where the vertical asymptote is an even multiplicity. So both sides have to go the same way. So since one side's going down, the other side has to be going down. If you don't like that, you can test another point. You can test x equal to -2. If you plug in -2, -2 minus 3 is definitely negative, and -2 plus 1 squared is definitely positive, and the negative divided by positive is a negative number. So we know we have to be negative if we plug in -2. It would be -5. So if I plug in -2, I get a y value of -5. So I'm way down here. Oops. Again, I don't think you need to actually plot that point, but you can just think about it if you like doing it that way. And then going that way, and then over to the left, getting closer and closer and closer to our horizontal asymptote. Which I know I didn't draw very well there. I feel like I could draw that better. There, that looks a little extreme, but I like it. Something to note about this graph, which I think is worthwhile, so you all will believe me when I say it. This graph crosses its horizontal asymptote. Right there, at that x-intercept. Totally valid. Totally happens all the time. So I really want to just point out, graphs definitely do cross the horizontal asymptote sometimes. We're not going to worry too much about it. In fact, we're going to see some graphs that might actually cross the horizontal asymptote. I don't expect you to find those points necessarily unless you kind of are forced to. But yeah, don't worry about them crossing the horizontal asymptote. Just be aware that a graph can and will cross its horizontal asymptote some of the time. All right. Let's look at this next example. Oh yeah. Yeah. Sorry. 5x squared over x squared plus 3x minus 10. Okay. Definitely we should do all the things. So let's see. I'm going to start with my y-intercept. X equals 0. 0 is 0 over some not 0 things. 0 over negative 10 is 0. X-intercept, set the top equal to 0. We get x equal to 0. Again, or maybe not again, but noting that the multiplicity here is definitely 2, meaning we're going to bounce. Vertical asymptotes. We're setting the bottom equal to 0. Hopefully it factors. It does. It factors as x plus 5 times x minus 2. So we're getting x equal to negative 5, x equal to positive 2. My vertical asymptotes. And they both do have a multiplicity of 1, meaning that they're going to do this opposite thing. So both these vertical asymptotes, one side is going to be going up and up and up to infinity, one side is going to be going down, down, down to negative infinity. And then finally, the horizontal asymptote. Let's see, the degree on top is 2, the degree on the bottom is 2. So the degree on the top and the bottom match. So that's going to mean that our horizontal asymptote is going to be, well, let's write the function here just so you can see it. F of x is 5x squared over 1x squared plus 3x minus 10. So our horizontal asymptote is going to be y equal to 5 divided by 1. Those are kind of all the features that we have. Now we're just going to put them all on the graph. Let's zoom out a little bit here, Jim. So I've got my origin. I've got kind of some big values here. So I'm going to make my marks a little smaller. 1, 2, 3, 4, 5. There's my horizontal asymptote at 5. And then I have vertical asymptotes at x equal to positive 2 and negative 5. Okay. So again, starting at the only point we have, if I move to the right, I can either go up to infinity or down to minus infinity. I don't have a good indication of which way to go. It's probably a safe bet to say we have to go down because it's probably unlikely that we're going to cross the horizontal asymptote without having to. It's still a good idea to check. So I plug in something like x equal to 1 to my original expression. 5 times 1 is 5, top is positive. If I plug in 1 here, 1 plus 3 minus 10 is negative. So I have a positive divided by negative, which is negative. You could actually do it, right? We could say f of 1 is 5 over 1 plus 3 minus 10, which is 5 over negative 6, which is negative 5, 6. So you could try to plot that point if you really wanted to. I'm just going to say, okay, I'm going to be negative this way. So on the other side of this vertical asymptote, and x is 3. We could plug in a point. F of 3 would be 5 times 3 squared over 3 squared plus 3 times 3 minus 10. That's going to be 45 over 8. I don't care what the value is. I just care that it's positive. Or we could have said the vertical asymptote had an odd degree or odd multiplicity, meaning we're going to do the opposite thing. One side goes down, one side goes up. And then as we further go to the right, we get closer and closer to the horizontal velocity. No reason to cross it, so I'm not going to cross it. I only really would say you should cross horizontal if you have to. Okay, on the other side, on the left side of this graph, we have to bounce off this x-intercept. So I kind of drew it maybe not very thoughtfully here. I should have come out a little more gradually. Say, okay, we're going to bounce off. And then we're going to go down this way because we have to. Or you could test some points. You could plug in f of -1. Then I'm going to get 5 over 1 minus 3 minus 10, which is still a negative number. Tells me I'm negative over here. And then lastly, on the other side of this vertical velocity, well, again, just like x equals 2 had this 1 up, 1 down behavior, x equals -5 also had the multiplicity of 1. So it's going to have this 1 up, 1 down behavior. One side goes up, one side goes down. Oops. And then as you go further to the left, the only thing left to do is get closer and closer to your horizontal velocity. Yeah. So that's kind of all, well, I should say, that's mostly all there is to graphing functions that have rational functions where the degree on top is less than or equal to the degree on the bottom. But we haven't had any examples so far, which we're going to talk about next class, of functions, rational functions where the degree on top is larger than the degree on the bottom, because then they won't have horizontal velocity. So that's kind of the next thing. But that's kind of all I've got. I will give you back 3 minutes of your life to enjoy Halloween with. So have a happy Halloween.